Hello, everybody. I am Tahereh Ramezani. I'm a Ph.D. student of Astrophysics. I want to explain you about one of my course with the name of star clusters. Its teacher is Dr. Ernst Ponce. He is my supervisor. I will explain you. If you have any question, you can ask me. If I know, I will answer you. If not, I will ask from my supervisor. Let me, with this series of lectures, I want to explain you whatever I learned from my courses, Star Cluster. So now I can share my screen and tell you. Yeah. Okay, here you see a star cluster. It's one of the open cluster or young clusters, young star cluster. You see in here how we can say that it's a young star cluster because it's in large major cloud, of course, because you see a lot of bright blue and white stars here. And also you see molecular clouds between stars. It means that still there are some stars that are forming in the molecular clouds. So we will still have some stars pull to stars that they want to be star. And these are also molecular cloud. Also, you see here, there is one red star. Why? Maybe you asked that why in the young cluster we have a red star. Because it is not in this star cluster. It is a star between us as observer and star cluster. So it is not related to this young cluster. What can we learn from star clusters? We can measure star clusters in two views. For example, we can consider each one of the stars in the each one of the star in the star cluster, or we can consider the whole cluster itself. So we have two views of star clusters. The star cluster as globular aggregate, if we consider the whole cluster, for example, one of the points that we say that we can consider the whole cluster as a cluster. If we consider that, we can have the distance, age, reddening, and metallicity, kinematics and dynamics, initial mass function. Maybe ask that what is initial mass function? It is a mass, for example, when you see here, for example, there are mass here and some stars wanted to born. They are proto stars. For example, they are not star now. For example, when we call something a star, when they are shiny. For the first bright that we see from the star in fusion, we call it a star is born. When it is not brightening and it is not shiny and we do not have the first fusion, we do not call it a star. So we have some protostars that are behind being a star. So initial mass means, for example, there is a mass here that we will, after a while, we will have some protostars and then some stars like these stars. And that we call it initial mass function. star formation, evolution, and global characteristics of a galaxy. The other view, if we call a star cluster as each stars, if we can say each star of a star cluster, we can measure the special star groups, like, for example, CP stars or chemical peculiar stars, blue stragglers, supergiants, binaries, Wolf-Rayet stars, variable stars, post-AGB stars, or HP stars, and so on. And we can test of most astrophysical models and theories. So what is star clusters? The star clusters are a group of stars that are they held together by mutual gravitational attraction. We call it a star cluster. The number of the whole star cluster in our Milky Way is about 10,000. But only we have 3,000 open cluster, and we have 170 globular cluster or old cluster. And also we can say that all members of an individual star clusters are born within one giant molecular cloud. As time went by, the scale of them is some of them born, for example, now, for example, some of them was born some few million years, but the whole of them, because in astronomy, million years, a few million years is not much. So we can call them, they are somehow are born in a same age. But all of them are born in the same giant molecular cloud. All members of an individual star clusters have some characteristics that are the same. For example, for distance, the whole members of an star clusters have the same distance. Age, they were born in the same, somehow in the same age. The metallicity of them is somehow is the same. Also the kinematical characteristics, they are like each other. Radial velocity, proper motion, others. We have a satellite that we call it Gaia, or Global Astrometric Interferometer for Astrophysics, or Gaia. With Gaia, we can measure the radial velocity spectrometer, resolution, spectral range, all objects greater than 17th magnitude, 150 million objects, and accuracy between 1 kilometer over a second and 15 kilometer over a second, depending on spectral type and magnitude. But the thing is, for identical kinematical characteristics, we can measure the proper motion of each stars with Gaia, somehow very accurate. But for radial velocity, no, we cannot measure them accurate. In this picture, you see the evolution of our astrometric accuracy during 2,000 years. For example, from 150 before Christ until the year of now. You see the evolution of the accuracy. And now with Gaia, it is somehow a new evolution. And we can measure many things very accurate. With Gaia, we can measure with an accuracy of 10%, with the distance in 10,000 parsecs. We can measure somehow the star in here, also Masaryk clouds. We can measure them, measure the proper motion, and the proper motion with the accurate to 1 km/s for stars up to 20,000 parsecs away until here. But for previous satellites, no, it was not with this accuracy. For example, they had an accuracy of 10%, but only up to 100% parsec. But with Gaia, we have 10% accuracy to up to 10,000 parsecs. Because the star is here, it is in one of the arm of our galaxy. We cannot see the star in another side of the galaxy. For example, if our star was here, if sun was here, we had a very good view for whole galaxy and the other side of the galaxy, but now not, because of the position of the sun in the galaxy. We cannot see the other side behind the galaxy. And you see the data for Gaia data release 2, which are here. Also for Gaia early data release 3 or Gaia EDR3. The thing is, there maybe we think that between two data release 2 and 3, we have some accuracy, like in errors. For example, we call it for extragalactic sources, but we do not have it here. The whole number is completely different. It is not the accuracy of a few numbers, a few percent of numbers. The whole number is different. So we should consider a new data release for Gaia. And we have something that we call it open cluster and globular cluster. But why we call them like this? Because in our galaxy, which is, Milky Way is a spiral galaxy, just for spiral galaxies like Milky Way and Andromeda or some other galaxies that they are spiral, we can call open cluster or globular cluster. But for other galaxies like Magellan Clouds, which they are not spiral, we do not call open cluster or globular cluster. We call them in general star clusters or young star clusters and or old star clusters. We do not call them open or globular, young or old star clusters. In here, you see the location of star clusters. For example, for globular clusters, we see them mostly in galactic halo, which is somehow far from the galactic center. Also, in the galactic bulge, we see a lot of globular clusters. In spiral galaxy, of course, it is our galaxy, Milky Way. And we see young or open clusters in a galactic disk in here. And the distance of sun until the galactic center is 8 kiloparsec. The whole of the galactic diameter is around 30 kiloparsecs. As I told you, we have globular cluster in galactic bulge and galactic halo. But the thing is, globular clusters, they are moving. They move from, for example, galactic bulge or galactic halo to galactic disk and then continue. They move. So maybe somehow they move near an open cluster in the galactic disk, and then they continue their path. But open clusters, no, they are not moving much. Also, as you know, each star in each cluster and also the whole cluster move, but they are moving around the galactic. But the open clusters do not move in the galactic halo or galactic bulge. They are moving the whole cluster around the galactic center, each cluster itself. But the globular clusters, they are moving into galactic disk and then continue their moving until they are around the galaxy. For some difference, I want to say some difference about open clusters and globular clusters. For open clusters, the age is around 1 million years to 5 giga years. And metallicity, they are the base is Sun, and we compare them with Sun. The metallicity for open clusters is -1 to +0.6. It is in logarithmic. And distance from the Sun is more than 45 parsec. And mass range of the members is 0.08 to 100 for a Sun. Total mass is up to 40,000 million of Sun. The absolute linear diameter is 2 to 25 parsec. But for globular clusters, these are different. The age is up to the age of the host galaxy. For example, we have globular cluster that is the age of the Milky Way. Maybe ask that we had the first galaxy or we had first globular cluster. And we can say for answer that we had first galaxy, and then in the molecular cloud that the star one, for example, star explode, it had the jet or shock, and then it formed a globular cluster, globular cluster, and then it is somehow it was first galaxy and then globular cluster, but the age was somehow near each other. So if you find a globular cluster, it is somehow the age of the host galaxy. Metallicity is the -0.5 to -2.5. It is also again in logarithmic. Distance from the Sun is more than 2,000 parsec, and mass range of the members is 0.08 to 20 million for Sun times of Sun. Total masses is up to 10 to power 6 million, and absolute linear diameter is up to 100 parsec. These are the star cluster for the first session. I hope it was useful for you, and see you next time. Bye.